I haven't gone live, that's why. Hi, my name is Bob Greenyer, and I'm a volunteer with the Martin Fleischman Memorial Project. So today we will be talking toroidal models of the electron and proton. Can you hear me, Tony Jaboni, Corky Goss, Terran Art? Can you hear me now? Yes, excellent. Thank you very much. Okay, so when I posted this image that you see here on the screen earlier today, in fact, about 40 minutes ago, Henk Uren said that he said, oh, that's a nice sort of image of what might have interacted with the copper pipe, the 15mm ball burn or ball lightning cut in his Vega experiment. And I said, yes, of course, it's a synthetic image, but we've actually shared images that look remarkably like this. And they're already public. There's many more images, and in fact, some of them are of higher fidelity, but the ones I'm going to show you now were already shared a good few moons ago. And here is one of them, and it's actually on this much larger image. And this is where Henk Uren was producing ball lightnings out of a tube, which we will talk about later. And they were detaching from the tube, moving towards this sheath, which is of fused quartz, and they were colliding with it. And behind this sheath was the anode. So there was kind of some sort of vector in there that was driving it. And sometimes you got these very geometric structures here with the balls around a central spot. But more often than not, you get these kind of structures. Now, it's still got a geometrical structure. And as we know, when the structures in the boundary layers between copper grains in those ball lightning cuts in the copper pipe, they actually produce these geometric structures in there as they are consuming the material. So it does make sense that they would have this geometric nature. Now, the way I'm reading these kind of ones is that the spherical structure, which has some hollowness to it, has collided here. And if you can imagine, you've got a ball, and the ball collapses down onto this quartz surface, which is ostensibly mostly flat, reference to the ball that's hitting it. Then on the outside, you've got like a Fresnel effect where you have more of this kind of worm-like structure interacting with the fused quartz, and you have less here where it's hollow, okay? And then there's something going on in the middle. So I see these as kind of geodesic spherical structures. Here's one that we know and love, where it collided with the structure but side on, but this is a toroidal structure. Now, I'll talk about this in another presentation where I believe that the collapse of cavitation bubbles are doing something similar, and it will shoot out a beam. But we've talked about that a number of times. There's some other examples here. So in this case, again, this is a spherical structure in my view with a hollow shell, and what you're seeing is a density around this edge where you've got a lot of impacting worms or these magnetic flux tubes. Then you've got a little bit less, and then you've got the hollow bit in the center, and you only get a little bit of effect because you've just got a little bit of the surface interacting with it. There's many, many examples of these strike marks, okay? But then there are some toroidal ones, and I believe that this is a toroidal structure. And again, around that rim where the ball lightning cut out the copper pipe, we had a toroidal one, which again was had this iron-rich crenellated structure on the outside with these little kind of vortex pair structures coming off them as tendrils. But in this case, the reason I'm saying this is a torus is because there's absolutely no damage whatsoever in this central section. Okay, so this to me is more like the ones that we saw in a different place on that cut, and it may actually be the case that this is also a torus here. But when I share the full data set of these, there are many examples, and they're actually at a much higher resolution than is even presented here. And when you go into them, you actually see that they are comprised of little tori, and sometimes it's quite clear that they are tori in rings, and sometimes that you can see, this is a bunch of clumps of structures around. I don't know. There's a lot to be thought about when this data, more of this data, is shared for analysis. Now, here is one on the kind of like the map of the pyramid, and you can see here there's this central section. This is a pillar, and then you have this area around here. So anyway, those are the kind of things. But where did this journey start from? Well, one could argue that it started from the work of Winston Bostick, and this is, I think, his 1957 paper, 1956, and he did these electrical discharges. This was deuterated titanium. This is a ceramic. He did these electrical pulses. It produced a flux loop between those, and as one can imagine, if you've got a current loop going through this plasma, then you will have this magnetic field going around it. And what happened was, as it came off, and that's just this jumping about, sorry about that, there was a magnetic reconnection on the end here, and it produced this torus structure. So straight away, you've got an electrical current going around here, and you've got this, what now is, rather than just the magnetic field going around a wire, let's say, it's actually like a poloidal structure. And when these things interact, they kind of deflect from each other depending on which direction they're coming from. And the experts that hopefully Andreas might talk a little bit more about this. But one of the things we saw in David Boutlier's experiments coming out of a ball lightning when it broke down is a plasmoid structure similar to this. In fact, extremely exactly similar to this. And so we've replicated these kind of effects. Now, these are actually hypotheses, and he's very clear that these are hypotheses for how these occur. And you can imagine that if this is open-ended and they come and twist together, you might get something like this. Or if you have two tori coming together, they tended to orbit around each other. And Bostick went on to do discharges on like a hexagon-shaped cathode, and this produced down its length a series of these structures where you had these vortex-anti-vortex pairs. And if you look at them in this diagram, which we spoke about before, this is actually in Maury B. King's book, and they're saying that this might be considered as polarization of the vacuum, and you've got a left-hand rotation and a right-hand rotation. So it produces a pair on one side, and these come together, and they come to a pinch point here. And this is actually the basis of LPP's fusion model. And it comes together in what they call a little plasmoid bundle here, and they argue that there's some neutrons being formed or something from the process that's going on in the particular experiment that's there. Well, Bostick continued to do this fusion-type directed research until about 1980, and this is a paper with Nardi, and in this particular image here, this is where the so-called D4D ratio came from, according to their work. And in their impact marks here, you see this toroidal structure with spokes around it. Okay? And I think this is very, very interesting. And this was one of the indicators, along with the work of Ken Shoulders, saying these multiple toroidal structures without ever drawing what they look like, and saying that they are like electrons, and they can have go down to a charge of -1, but they can be fantastic numbers of electrons in there, stabilized by 1 in 10,000 electrons, 1 ion in 10,000 electrons, and they stabilize the structure, because you'll be aware that normal exotic vacuum objects, they fall apart. Normal heavy electrons like a muon or a tauon, they have very short half-lives. They just decay quite quickly, whereas an EVO relatively lasts for a very long time, and so something has to keep them stable. And one can argue what that might be. But when I saw these various things, that led me. I had that in my context, and when I saw these things on the Hutchison fracture sample, that led to a fractal model of the exotic vacuum object, which, because it's meant to be basically a cluster of electrons, the assumption is that the electron is like that in a self-similar way, and because Bostic had said in 1957 in his public addresses that these things could be all the way down to subatomic particles and all the way up to galactic objects, I was of the mind to take him seriously and say that this could be a way that the universe is structured. And the other thing which we're going to be talking about a little bit today is the Aharonhof bomb effect, or rather the equations. Perhaps that will be addressed, I don't know, but I will be talking about that in my presentation in ICCF 25 in Poland. And if I can go to this actual link here, rather than it just allowing me to edit it. No, it's not going to. Go to the bookmark. Okay, it's not going to do that. Down here in this paper by, it's by Afanasev and Dubovik. And I have to say again, Dubovik is really at death's door right now. It's a real shame that we're going to lose him at this time when so much is being found and discovered of his work. But down here, there's something that I think is very, very interesting here. What they're doing is there's a screen here, and there's a beam of electrons, and we have our fractal toroidal structure here. And it's saying here, the magnetic time-dependent Aharonhof bomb effect. For the charge current configuration discussed in the text, the time-dependent magnetic flux differs from zero only inside the impenetrable torus T. Outside T, the independent of time electric strength E differs from zero only inside the torus hole. It is the time-dependent magnetic flux inside T that leads to the time variation of the intensity of the scattered charged particles, right? So anyway, we've got charged particles coming in here, and they are scattered, and you can see that there seems to be a concentration in the center. And this is, it might not make sense now, but this is why I believe that you get these things like was observed by Slobodan Stankovic, by Klimov, and when you're using HHO to cut through very thick, like 50 centimeters of steel. And I will talk about all of these things later time. But to my mind, it is partly to do with this and partly to do with the fact that the AB effect helps the coherence of the matter that it, and in this case, it's electrons to form a coherent matter wave. So I don't know whether Pavel will be able to join us, but he has this model of both an electron and a proton. The electron is a fractal toroidal structure, and it's very specifically a fractal toroidal structure of toroids. The model of the proton is actually a fractal coil, like we've spoken about in the Bagel game. So I hope he'll be able to speak to us on where he got his inspiration from. And his inspiration was from, I think, 2007 or 2008. But he's not the only one. There are many scientists out there, a lot of Russian scientists, and I have other papers from those. And I was given one in California before I introduce Andras Kovacs. And I've got it over here, so I'm just going to wave it. I don't know whether you can see, but it's by a guy called, and I had his name earlier, somewhere here, by James Carter. It's from 1993. Here you go. And it has a whole periodic table. It's a whole periodic table of toroidal atom structures. And this is exactly what Pavel Asmir has done. He's actually got a toroidal model for kids to learn how these structures go together. But on the bottom here, there is, in this particular example here, there is a torus. I don't know if you can see because my camera's in the way. This one here, there at the bottom. And that, in fact, is a coil of a coil of a coil of a coil structure. And that was in 1993. So when the Russians were doing this was also being thought about in America. So Yeah, so you're not seeing the camera image. Okay, so for those on YouTube. So, firstly, I'd like to introduce Andres Kovacs. Andres Kovacs is Hungarian. He was born, I think, near where I am currently right now, and I will switch the screens around so people can see you on YouTube. Give me a second. Quick, that one. Cancel. And he is working with one Giorgio Vassallo, who actually, thank you, Giorgio. He was one of our first $1,000 donors in 2012, I believe. So, and I'm not doing this because of that. He's been a follower right from the beginning and contributed at key points. And now he's been working, producing a book with Francesco Celani. You might remember from our early replications in 2012 and 2013, the wonderful Francesco Celani, the first LENR scientist to seriously allow someone else to test his work, and thank God he did. And he's then actually now working together. Andres, is that right? And so, yes. Andres, can you give a little bit about your history and why you're interested in this field? And then you've got the floor.
All right. So I have been studying physics at university, and at that time I thought I will be a physicist. But then, life have decided otherwise. So I was doing other works, and after a big detour, now I'm returning to physics. But I'm not in at any university or research institute. So I'm in a lucky position that I can choose myself, what I would like to study and what I'm interested in doing. And I have been interested firstly to replicate Parkhomov's reactor. So when I read about Parkhomov's reactor, I thought, well, this looks a simple enough experiment. So then with some colleagues we thought, well, we can do this. So let's see if it works. And the Parkhomov replication has been my entry into LNR. We could not replicate what Parkhomov has found, but we saw other strange phenomena in that type of reactor, including elevated Geiger counter readings. And well, elevated Geiger counter readings, it certainly sounds like nuclear. So then I have been interested to understand what is really going on here. And then Francesco Celani introduced me to Giorgio Vassallo, and I thought that he's a genius, and I have been inspired to work together with him, and that has led to writing the book together.
So the name of the book is?
It's a unified field theory and Occam's razor, but I will have a slide about it in my presentation.
And this bit that you're going to share tonight isn't actually in the first edition of that book, is it?
The part about electrons is. So everything that I say about electrons is in the book, and then I will have a part about the protons. The proton part is brand new, so that's not in the book, but it is in an open source or meaning an open article, so anybody can read about what you write about the proton.
Okay, fantastic. So do you have anything to add before going ahead with the presentation?
All right, so I share my screen. Okay. There. So do you see my screen?
I do. It's lovely.
All right, great. So I will be talking about the results of our work that led us to the toroidal models of the electron and proton. So this has been mainly my work with Giorgio Vassallo, but the other co-authors with whom we have been working are also listed here. So I would like to begin with a history lesson, a little bit similar to how you did. It's important to set the context. And I will start with electromagnetism theory development to really understand what are the historic trends and from where we are going, where we are heading to. So the history of electromagnetism really goes back to 1850s. Michael Faraday has been the first to develop the intuition about electromagnetic fields, and he has been the first, as far as I know, to formulate the electromagnetic nature of light. But he could not put it into equations. Well, the first one who put it into equations is James Maxwell, who introduced the equations now named after him. But the version that we learn in school has been actually written down in 1884 by Oliver Heaviside. So he organized Maxwell equations into 4 vectorial equations. And what Oliver Heaviside wrote down is basically what I have learned in high school. And if somebody's physics career ends in high school, then this Heaviside equations is what you're really learning. Now, in these equations, what is important to keep in mind is that charges, they remain as an external objects put into the equations by hand. In other words, the equations themselves do not tell you what charges are made of. Okay, then next step in this theory development happened at the turn of 20th century. Linard and Wiechert developed a formulation starting from the 4 potential. This is a vector object. And then the electric and magnetic fields are derived from this 4 potential object. So this approach allows one to write Maxwell's equation as a single equation. So that's quite a good step forward. Now we have only one equation that describes all of electromagnetism. And this is the formulation that I have learned at university. And today, I believe still physics students learn this 120 years old formulation of electromagnetism. Now, all of this that I told up to now has been a fringe theory when it was formulated. So these people, it's been a small community. They have been interested to work together. So this is important. But the famous and respectable scientists did not teach electromagnetism at that time. Sometimes they just mentioned it in passing as an interesting hypothesis. Because at that time, the ether particles was all the rage. And self-respecting physicists of the 19th century, so that what you have to do is to study ether particles. So it actually was only around 1910, 1920, when radio engineers started using Maxwell's equations. And then it had to go mainstream because, once it's commercial, once engineers are using it, the physics community has to follow suit. And this, I think, for our community is also important inspiration that this is really how big innovations happen. First, it's a fringe community, there is a useful application, and then it goes mainstream. That's, I think, is the usual way. Now, once this electromagnetism theory went mainstream around 1920s, it was then considered to be a closed and completed chapter in physics. And pretty much we learn today still the same way about electromagnetism, how it was then codified in the 1920s. Okay, question: has there anything that happened since then? Well, there actually has been a few things. So let's look now at the further development since the 1920s. There have been 2 important steps forward that happened in 1950s. First, what you can see on the left side is Hungarian mathematician Marcel Ries applied the Clifford algebra to study electromagnetism. And it takes some learning to get familiar with geometric algebra. but it's not that impossible. I'm lucky that I have a colleague who is a mathematician, and I asked him, "Can you explain me Clifford algebras?" And he was explaining quite well in 2 hours. So that I believe if you have a mathematician friend and you invest a few hours, you can learn about Clifford algebras. It's not impossible. And the point is that once you learn it, you can work with a formulation that is very well suited to describe space-time events, and then you don't get lost in notation of big, vector matrices, but you will, sharply see the dynamics without getting lost in the notation. That's the point there. And then Ries's work has been further elaborated by David Hestenes, Lonesto, and many other mathematicians. So this is really a growing trend that's now reaching critical mass to apply Clifford algebra to describe electromagnetism. Okay, the other important event in 1950s is that a physicist, I think he was an American physicist called Moses, attempted to formulate electromagnetism as a pure field theory, meaning that he wanted to work with field objects that incorporate both charges and electromagnetic fields, so that charges would not be somehow separate and external from the theory. And well, he had some success, but did not become mainstream. But what did become quite popular starting from 2000 is to study longitudinal or scalar electromagnetic waves. And I think your audience is quite well aware of some of these names. And there is, again, a growing community that does believe, both on theoretic and experimental grounds, that there are longitudinal and scalar electromagnetic waves. Now, to do this theory of scalar waves, one can do it either complicated or simple way. Complicated ways to make Maxwell's equations more complicated with extra objects. Simple ways to make them more simple. And all of these developments, I believe, kind of culminated in around 2017. So two Italian gentlemen, Giuliano Bettini and my co-author Giorgio Vassallo, have developed the simplest formulation of Maxwell's equation that you can see here on the screen. And they developed this formulation using all of the above mentioned trends. And I think that's a really important step forward when you have a decades-long development, and that results in a much simpler understanding of electromagnetic theory. So let's see what this simple equation really says. This A with the square is the four potential vector. The square signifies that it's a vector in the four-dimensional space-time. And the sigma is just the space-time derivative, but this multiplication between them is the Clifford multiplication. Clifford multiplication, you can read about it in our works, is the proper way to do the multiplication in space-time algebra. So this is a very compact notation. Oh, sorry. So what this notation really says here is that if you have the four potential object, which is the fundamental object in electromagnetism, you take its space-time derivative, you have the electromagnetic field, that's G. This electromagnetic field incorporates electric field, magnetic field, and scalar fields. So there are all three types. And then you take the space-time derivative of this electromagnetic field G, and you get 0. And that's it. So it's simple enough. Okay, is it oversimplified, or is it the real essence of electromagnetism? So we believe that there is no oversimplification here. There is no need why nature should be more complex, needlessly complex. This simple equation is, in fact, the essence of electromagnetism. But the simplicity, in a way, then allows many different solutions, because simple equation doesn't mean one solution. A simple equation can host many solutions, some of them which we didn't know about before. So here I listed some important consequences of this simple equation. So the first consequence is that the electric and magnetic charges are no more external objects to Maxwell equation, but they are an integral part of the electromagnetic field. So this is, I think, philosophically very important, because for the first time, we can answer what electric and magnetic charges are made of, and they are made of the electromagnetic field itself. So in that sense, this formulation completes the Moses program. And these charges, they are related to the scalar field. That's described in our work. What also follows from this, you can see that this is a wave equation type formulation. So what follows is that both fields and charges are somehow part of an electromagnetic wave, and these waves always move at the speed of light, which means that all electric charges move at the speed of light. So the electron that looks to us, this slow particle, is in fact moving at the speed of light, but this fast moving of speed of light is called Zitterbewegung. And that's again not a new idea. Schrödinger and Dirac have recognized this idea already, but it has been challenging for them to put it into equations, and this now directly follows from this Maxwell formulation. The other consequence is that longitudinal scalar waves now become a trivial solution of Maxwell's equation. And I had some lecture about that earlier. I think it's posted on your channel, so people can look it up. And then that again shows that to describe longitudinal waves, we don't have to add any complication. It's just a trivial solution, just like transversal wave is a trivial solution. Now, of course, every wave behaves very differently depending on its wavelengths. So if you have an ordinary transversal wave, if it has long wavelengths and radial wave, it becomes very different than if it has short wavelengths and it's a gamma wave, right? So one passes through walls, other one reflects from metal objects, and they need different type of sensors to detect, and everything is different. And it's the same for longitudinal wave, and the low frequency and high frequency ones behave differently. And I came to the conclusion that what physicists call a high frequency wave, what physicists call a neutrino is in fact a high frequency longitudinal wave. So that's my perspective. And again, if someone's interested about the details, we describe in the book how I came to this conclusion. And keep in mind that so far all neutrino measurements show it traveling at the speed of light. There's never been any neutrino detection slower than the speed of light. All right, but let's focus on our subject of today. So this is the foundation somehow to what we will use. And with this foundation, we'll try to understand better what the electron and proton are made of. And I strongly believe that once we are successful and once there is engineering applications, then this will become mainstream in electromagnetism. So maybe 100 years from now, this is the type of electromagnetism that people will learn at university. Now, the other thread that comes into my presentation that's very important is the article which Bob has translated, the Bagel game article. This has been introduced in your previous videos. So this article describes an experiment that creates a persistent electromagnetic structure. So what you see in that experiment is a kind of a torus upon torus upon torus structure of the electric wire that you can see there. And then by applying AC current into that interestingly coiled multi-torus wire, one gets this electromagnetic field configuration illustrated at the bottom left. And in this configuration, electric and magnetic fields induce each other in an interesting way. And this induction is persistent, so that if you turn off the current source, there is a persistent electromagnetic field that stays there. Okay, big question. Did the people doing this experiment created a particle? Well, this electromagnetic object, it certainly has energy, and if it has energy, it has a corresponding mass, equals mc squared. So in many ways, this fulfills the definition of a particle, but they use a very low frequency, and they did not have to choose very particular sizes. So it means that in the low frequency region, if this is a particle, there are infinitely many particles, perhaps. And then the quantized particle masses that we are familiar with, they only appear in the very high frequency region, and we will see the electron frequency a bit later on. So if this we can think of as a particle, okay, this is very interesting because we can understand its electromagnetic structure. We can calculate from Maxwell's equation how induction happens inside. So if a particle has electromagnetic structure, can we apply the same approach to the electron to somehow find out what is its electromagnetic structure? And this actually has been a long-standing desire in physics. We are not the first with this idea. So already Fleischman had this quote, which I will now read. Many attempts have been made, and some of the theories were even able to arrange things so that all the electron mass was electromagnetic. But all of these theories have died. So this approach is a graveyard of theories, we can say. But we are not discouraged by these failed attempts, but we try to learn from past mistakes. So with this inspiration of the bagel game experiment, let's see what we can say about the electron. Now, when we describe a physical object, it is important to base our description on actual physical measurements and experiments. And unfortunately, there are very good measurements that tell us exactly how big the electron is. However, what is confusing is that these measurements give a very different size for the electron depending on the type of measurement. So the first measurement we can use to get the electron size is the Compton scattering type of measurements. So Compton scattering measures the radius of a spherical charge, and this can be calculated according to the Klein-Nishina formula. So the experimental results from Compton scattering experiments is that this electron has a spherical charge with 2.82 femtometer radius. And this is called in physics the classic electron radius. Okay, so this Compton scattering is done with very high frequency waves, but you can do another type of scattering experiment with low frequency waves, and this is called Thomson scattering. When you apply low frequency waves, you are measuring the whole radius of the electron structure, and the experimental result here gives 386 femtometers. In physics, this is called the reduced Compton radius. So I illustrated it here with this RE radius. So somehow the spherical charge is moving inside this much bigger electron structure. And then finally, we know that the electron spreads in a wave function, and this spreading in a wave function is according to Heisenberg uncertainty. And the most studied spreading of the wave function is in the atomic orbitals. And the experimental result for a ground state with elementary charges, one positive, one negative, is the well-known Bohr radius, which is 52.9 picometers. So we can consider these three different measurements give three completely different electron sizes. Wow, that's confusing, but there is a very amazing relationship between them. So if you look at the ratio of the classic electron radius and Compton radius, the ratio is alpha, where alpha is the fine structure constant. And again, you look at the ratio of the Bohr radius and reduced Compton radius, you again get this alpha ratio. So it's some kind of a geometric structure, and that's not a coincidence, right? So we have to understand, what does nature really do when it creates this embedded geometry of very different sizes, and this alpha is what in physics is called the fine structure constant. It's approximately 1/137. So from this picture, you can understand why many physicists have been obsessed with this number 137 over the past 100 years. Okay, now it's important that when we describe the electron, we base ourselves on these numbers, because as long as we want to describe reality, these numbers give the boundary condition. So if you talk about something completely outside of this boundary condition, you're not talking about physics. So to put it bluntly, there are many particle physicists who say that the electron is an infinitely small abstract point. Well, that doesn't have any relation to these numbers, so that's not physics as far as I'm concerned. So what we'll do is keeping with these real measurements, and we try to understand how an electromagnetic structure conforms to these numbers. So if we imagine that the electron is an electromagnetic structure, then there must be electric and magnetic fields that induce each other within the electron, the same as with the bagel game experiment. Okay, a charged object has electric energy lines around it and corresponding electric energy density. Okay, there is a well-known formula. You take the square of the electric field and multiply by dielectric constant over 2. So we get these numbers from Maxwell equation, and electric field goes down as 1/r squared, then you square it, the density goes down as 1/r cubed. And to get the total electric energy, we have to integrate this density from infinity all the way down to the radius of this of this sphere. So here is this integral, radial integral of the electric energy density. So this is quite straightforward math. I think people can verify this as a homework that this calculation is correct. So when you multiply it down to a radius r0, then putting in the classical electron radius, this one value that I mentioned was measured by Compton scattering, we see an amazing result. We see that the electric field is exactly half of the electron mass. Exactly half. Amazing, right? So this gives then the physical meaning of the electron charge radius, that the electron charge radius is this real physical quantity, and the electric charge is distributed over the sphere, and the corresponding electric energy is half of the electron mass. Now, we remember that every charge moves at the speed of light. So we take a model where we have a circular Zitterbewegung around this circle, and then we can calculate the corresponding magnetic energy of this current from the current loop formula. So the current loop formula is that the magnetic energy is 1/2 times magnetic flux times the current. So the magnetic flux is quantized to h/e, and the current you can calculate from the light speed motion of this charge, and you get this formula. So now into this formula, again, quite straightforward calculation, we put in this reduced Compton radius that was measured by Thomson scattering. And again, amazing, the magnetic energy is exactly half of the electron mass. So now we get the physical meaning of reduced Compton radius. It's the radius of the electron Zitterbewegung. Okay, we put together the electric and magnetic energy, and together they give the total mass of the electron. So this means that the electron is, in fact, electromagnetic field, where electrical and magnetic field induces each other, and electron mass is just electromagnetic energy. So electron is trapped light, to put colloquially, and we are all the children of the light, to put it a bit poetically. All right, so this I think is a very important result. What is also you can see here is that in both electric and magnetic formulas, there is a dependence of 1 over r. So it means that the energies are inversely proportional to the radius. So it means that the more you shrink down the particle, the mass grows correspondingly. So heavy particles are really small, light particles are large. So let's keep it in mind. It will be important later for the proton. Okay, now here this picture is a static snapshot, but I told you that electric and magnetic fields induce each other. And in fact, we can think of an electron as an LC circuit. So the inductance L, we use the usual formula of flux over current. This is the inductance formula for a current loop, and we get this inductance value. We can calculate the capacitance also from the usual capacitor formula of charge over potential. And the potential we can calculate from the size of the charged sphere, and we get this value. And for an LC circuit, the frequency is 1 over square root LC. So the electromagnetic frequency of the electron is this value. It's about 10 to the 20 hertz, quite fast frequency. Now, in 1924, de Broglie had this hypothesis that every particle has an internal frequency proportional to its mass. So this de Broglie's formula is that h times his frequency is the mc square. And if a positron and electron annihilates, then the resulting electromagnetic radiation indeed has this frequency. And amazingly, this frequency, which de Broglie had this formula for, and which we can see in electron-positron annihilation, is exactly this number, which is the frequency of the LC circuit. So this, again, demonstrates that we are seemingly on the right path. The electron's internal frequency, which physicists call de Broglie frequency, is nothing else than its electromagnetic oscillation frequency. So you can see that we are getting towards the bagel game. Now, a question, is this toroidal so far? Well, if we think of the circular motion, okay, that's just a circle, but if we think of the electron having a size, then this sphere moves in a toroidal volume. So that is, in that sense, the electron Zitterbewegung is a toroidal structure. But there is more to it, because if we consider wave-particle duality, then we know that the electron wave somehow has an orbital motion when it's in an atom. In other words, this picture I showed you here is the picture in the rest frame of the particle. This you see when you move together with the electron. But if you're observing from the lab and you see the electron moving, then this circle really becomes like a spiral. And in case of atomic orbital, the spiral becomes a closed torus. So coming back to this toroidal model, if we consider the Bohr orbit model, and we consider this orbital motion of the electron in the Bohr orbit, which is a stable state of the electron, then we have a two-Tor structure in the language of the bagel game article. We have this internal Zitterbewegung loop and the bigger orbital loop. So very well we can see that the electron has a two-Tor structure in the hydrogen orbit. Of course, one could say that, yeah, it's more complicated because the Bohr orbit is a simplification. There is a radial standing wave. Yeah, okay, there is it's in that sense a more complicated object. But the point is that we seem to be on the right track here, and we can make the model more elaborate by also considering the radial standing wave. But anyhow, whether you consider it or not, the Bohr orbit, the simple Bohr orbit already gives you the correct energy levels of the hydrogen atom. What else is important? That we can also understand right away what is the electron spin, because when you have the Zitterbewegung motion, then it has the associated magnetic moment, and the electron spin is nothing else but the magnetic moment that's associated with this Zitterbewegung motion. So we can very precisely understand what the electron spin really means. Also, we can understand quite well what is the wave function of the electron. So when you have from the rest frame the Zitterbewegung motion, that's an oscillation in time. When the electron moves, then you have a Lorentz transformation into a different frame. And as you know, Lorentz transformation is mixing time and space components according to this Lorentz boost rotation. And the phase of the wave function is just the Lorentz transformed component of the Zitterbewegung phase. So once you understand Zitterbewegung and Lorentz transformation, you can automatically calculate and understand what the wave function really is. And I think this is, in that sense, important, that once we go into this direction, then quantum mechanics becomes understandable, because when I learned quantum mechanics at university, we started with postulates. You learn that this, and this postulate is the basis, and then you calculate things from those postulates. But you don't know where those postulates come from. But now we have a chance to derive those postulates and really understand the meaning behind quantum mechanics. So in that sense, we can explore not only the electron's internal structure, but also the meaning of the quantum mechanical wave function. So this is, in essence, what our toroidal electron model is. And now I just list here some related works. So if somebody is interested to learn more about our electron model, we have this book published with World Scientific called Unified Field Theory and Occam's Razor. You can see its cover. And basically it goes into more detail on all of these topics, what I described up to now. In addition, we give an understandable explanation to spinors, which as a university student I could never understand, but now you can. Pauli exclusion principle, Aharonov-Bohm relations, and longitudinal waves. Also, I have a video tutorial, Quantum Mechanics Introduction. So if you search this in YouTube, together with my name, you will see the video, and you will have there a derivation of Schrödinger equation, about quantum mechanical wave, and importantly about single frequency emission in quantum mechanical transitions. So when you have a transition between two quantum mechanical states, let's say two stable states of the electron, those transitions always generate single frequency waves. And this has been the inspiration of the so-called photons. And that has been also 100 years of uncertainty how to really understand photons. I think if you are patient enough and look this video to the end, you could have a chance to understand photons as well a bit. Okay, so this about the toroidal structure of the electron. I think I will take questions at the end, but now I will move on to the proton. And the big question is that once we have this interesting structure of the electron, can we apply the same to the proton? Well, let's start from the same principles. First, let's clarify what is the proton size. And again, we use the same method. We firstly consider what do Compton scattering say about the spherical proton size? And here I have experimental data of the Compton scattering radius, and this is a function of the frequency. Now, here the situation is a bit more complicated than in the electron case, because at these high frequencies, you have also particle pair production that gives extra scattering amplitude. So, for example, this peak is well recognized as the pion production peak. Okay, but we are not interested in pion production, we're interested in the actual proton size. So we have to look at the low frequency part of this chart before the pion production. And here you can see on the chart that if the proton was, for example, 0.005 femtometer, then this would give a too large radius with respect to experimental data. Now, if we demand that experimental data is well converging to the Klein-Nishina formula, then the actual proton spherical radius size, the charge radius size, comes out to be 0.0015 femtometer, very, very small value. And now I would like to note that this is not mainstream interpretation. This is our interpretation of these experimental data, but I think it's a very direct interpretation. You take Compton scattering at this region, apply Klein-Nishina formula, and you get the spherical charge radius. What is mainstream is the mean radius of the proton structure, and there are two methods to determine it, scattering and spectroscopy. Here you can see the scattering distribution based on JLab data. So somewhere in this region is where the proton structure is located. So this looks a bit like a cross-section of a torus. And both of these scattering and spectroscopy methods give about the same proton radius. This is what the physics literature calls the in quotes proton radius, the 0.84 femtometer. Okay, so we are trying to understand the proton as a structure that has the mean radius of 0.82 femtometer, within which this very small spherical ball is moving around. All right, now a logical question to ask, is the proton just a scaled down positron? No. For example, it's well known that the muon can be imagined as a scaled electron. Can we do the same with the proton? The proton-positron mass ratio is 1836, about that. And as I showed you in previous slides, with all else being equal, the particle size is in inverse proportion to particle mass. So from this mass ratio, okay, let's calculate what the scaled proton size should be. The radius of its charge is actually well matching experimental data. Okay, it's good. The toroidal radius should be 0.21 femtometer, and the magnetic moment scales down to the so-called nuclear magneton value. The nuclear magneton is just the proportionately scaled value of the magnetic moment. Now, the experimental data, as you can see from the spherical radius, it matches. For the other two numbers, it's same order of magnitude, but doesn't really match. There is a factor of 4 here and factor of almost 3 here. So these mismatches mean that the proton is not just a scaled positron. We have to consider another structure. Okay, now there is experimental indications, and you can see a reference article here already more than 20 years ago, that nucleons, they have actually a toroidal or anapole magnetic moment. So if you have a structure which has a toroidal magnetic moment inside, it's logical thought to think of it as a toroidal structure. So this very simple thought inspired us to consider the proton to have a toroidal structure, and that's why in our article we consider the proton to have a toroidal Zitterbewegung that's illustrated here. So So remember that in the electron, Zitterbewegung was a simple circle, and here the Zitterbewegung is along the surface of a torus. And there are actually two ways to construct this model. One is a rotating heavy positron with a single magnetic flux. So you imagine a positron, heavy positron being here, and then it rotates around, it creates a structure like that. The other way to construct this model is to say that the positron and proton are topologically different, and we consider the proton to be a 3-Tor particle with a distinct magnetic flux in the poloidal and in the toroidal direction. So in the article that we have, we consider both of these options, and then we calculate the corresponding numbers. So for the first option, the rotating positron model, we get the spherical charge radius being this before mentioned value that matches, poloidal radius 0.21 femtometer, and toroidal radius about 0.6 femtometer, and the magnetic moment we take as an input parameter. Okay, in the other example, the 3-Tor model, we get the spherical radius, charge radius with the experimental matching number, poloidal radius 0.46 femtometer, and toroidal radius 0.83 femtometer. And these numbers are actually really nicely matching the experimental values. And again, we take the magnetic moment as input parameter. And I know that I have now a revision in progress that will be published in the future, where we calculate the magnetic moment as well. So all of these parameters will be calculated, and they seem to be matching experiment. So that somehow is a good sign that we might be on the right track with the proton model. Okay, now let's consider how the actual proton motion looks like in the hydrogen, keeping in mind that as any particle, the proton also has a wave function, but it's much smaller. And it's well known that in the hydrogen, it's actually, electron is not moving around exactly around the proton, but the electron and proton move around their respective center of masses, like a sun and planets. And this fact that they move around their center of masses is actually experimentally measured in the hydrogen Rydberg constant value. And from the electron-proton mass ratio, it follows that the Bohr radius of the proton's orbit is about 28 femtometers. So what we can see here, and you have to use a bit your imagination, is that the proton charge now moves along a 3-Tor trajectory. So it has its poloidal circle, then the toroidal Zitterbewegung circle, and finally the Bohr orbit circle. And these 3 toroidal structures are embedded together, and we can see that nature is like the bagel game. This is really how real particles are structured. So those who made that experiment, maybe they did not know, but their experiment exactly reflects how elementary particles move in reality. Okay, then last question one could ask, what does this all imply for the neutron? Well, if we consider proton to be a single particle, it automatically means that the neutron-proton difference is the presence of a negative elementary charge in the neutron. Okay, we are not the first ones to think of that. Many people have thought of it and share this view, including Bob, and I think many in the audience. But again, the big question is what it precisely means in terms of structure. And to explore this, I use again Compton scattering. And by analyzing Compton scattering, I came to the conclusion that the radius of neutron's negative charge is 0.4 femtometers. These details will be described in a future publication. But graphically, here you see the proton structure I explained before. And the neutron is the same as a proton, except that you have this relatively large negative charge that's locked inside this toroidal structure. And these two charges together create the neutron. Now, please keep in mind that although neutron has two charges, these two charges have overlapping magnetic fields. And even though it has two elementary charges, for practical purposes, it behaves like a single particle. And in fact, the more you study these topics, the more you realize that the line between a single particle and multi-particle is a bit hazy. It's not always so easy to determine where you have the limit between one particle structure or two particle structures. And in fact, this has been the topic of last year's Nobel Prize in Physics, the so-called electron-electron entanglement. And what electron-electron entanglement means is that in some sense, the two electrons that share the same orbit are in some sense one particle, and they behave entangled as a single particle even if they are separated. So something a bit similar, I believe, in the neutron. You have two charges, but these two charges together form a single particle that eventually decays into a proton and an electron. Okay. And here are proton-related works. So we just published the article together with Giorgio Vassallo called The Proton and Occam's Razor. It's in this Journal of Physics published, so you can search it in Google. And actually, the publication of this article has been the inspiration that inspired Bob to invite us to this presentation. So thank you for inviting us. And the forthcoming articles will go more into the proton and neutron structure, and they will be titled, "What is the proton made of and what is the neutron made of?" I think this is my last slide. So thank you for attention, and if any questions, then they are welcome.
Thank you very much, Andras. Okay, so I've got at least one question here on the Zoom chat by Stephen B. Halls. And he's saying, is Zitterbewegung motion just the orbit circle around the proton, including the slinky-like helix? Or is it an embedded property of the electron itself, I assume?
Yeah, it is the property of the electron itself. So let's go back to that slide. So the Zitterbewegung motion is this toroidal motion, this circular motion that you see here. I hope you see my mouse. So this blue cork-like line is the Zitterbewegung motion, and you can also see here in the illustration two electrons with two energies. So the more fast the electron moves, the more the Zitterbewegung cork is like a spring pulled out, and the more slow it moves, the more it's compressed together like a spring again. And the orbital motion is the white circle. So this blue circle and white circle is what I refer to as the two-Tor structure. And remember, the Zitterbewegung is the blue cork, and that gives the electron spin.
Okay, I'm just seeing if there's any questions on YouTube. We have nearly 50 followers on YouTube at the moment. And I don't quite know how many we got. We got 14 participants in the room here. There are some across the two. Okay, so I've got some general questions that are not regarding your presentation. Do people want to ask questions in the Zoom call? If you want to raise your hand. If anyone wants to raise your hands, you go down to the bottom, you go click on reactions, and you click raise hand. Okay, Stephen, do you want to take the floor, please?
Okay, I was referring to the paper in 2023. Darn it, I've just lost my graphic. There we go. I was just wondering about, is B0 showing on my screen there?
Okay, do you want to share your screen?
Angle?
Do you want to share your
moment,
screen?
I stopped sharing and
So, Stephen, do you want to share your screen?
I can maybe try to figure that out. Hang
Down
on.
at the bottom, click on share screen and choose the screen that you have.
Are you seeing that now?
I'm seeing something shared. Yes, thank you.
Okay, so this is from Andres' 2023 paper. There's a black arrow that's pointing at LP and a blue arrow pointing at BE. Is that a precession angle of 60 degrees?
Yes, exactly. And this figure illustrates how nuclear magnetic resonance technology works.
And that is sort of a fixed thing that's always at 60 degrees?
Yeah, that is one property of nature that in quantum mechanics, this comes out to be always 60 degrees.
Thank you. I didn't know that. That's wonderful. Done.
Could you explain why that interests you, Stephen, about your background?
My background?
Yeah.
Well, I need to look for angles found in symbolism, and I had a career as a radiologist with MRI, so I know some of this physics, but we're relearning it all properly now.
Thank you very much for your question. Is that all you wanted to ask?
Yes.
Okay, so if you can mute, unshare your screen, and then I will invite Chris to make a question.
Oh.
So get down the bottom again, go to share screen and go stop sharing. Or it might be on the top of your thing. It says the top, there's like a green area and you can go stop sharing on the Zoom interface. There we go. Thank you. Right, Chris.
Thanks for
cheers. Do you want to take the mic there, Chris?
Hi, Andres. Thanks very much. Hopefully you can hear me. So I've had your book for a while, and just it's taken me a long time to basically go through it. But one of the things I'm interested in is looking at the neutrino physics, and especially how they wrap themselves up in the same way as what you've described, the electron and the protons. And the data seems to fit really well with the massive neutrinos that Parkhomov's looked at, and to the point where the neutrino charge radius comes out like right inside the bracket of the measured charge radius for like a 23 EV neutrino. So I think that's one really cool thing. But my question to you is, have you looked at the Vorton structures that Freiberger had talked about? I think I'd sent you the papers a while ago.
Yeah, exactly. You did send me some articles. I'm in the process of reading them. And well, to answer your question, I answer a bit similar way how I answered in our email exchange, that although I stated that from my perspective, what physicists normally call neutrinos, they are these trivial longitudinal waves. It does not mean that those waves could not create in turn particles. And this is very similar how you have a ordinary transversal wave, whose transversal formulation is well known. Well, it just boringly travels in flat space-time without anything happening to it. But once it travels close enough to a nucleus where you have a strong electric field, then it suddenly can create an electron-positron pair. So the trivial solution becomes an electron-positron pair. And I imagine that the same thing could happen to longitudinal wave. You have a trivial solution traveling at the speed of light, and close enough to an atom, it could create some particle pairs, which you can call neutrino-associated particles if you wish. But these particles,
100%.
I have not studied these. Who knows what particles they are?
Yeah, and the other thing about that is, if you look at take the longitudinal neutrinos, if you look at a maximally dispersed wave function, so the cosmic neutrino background, then the self interactions will be like an Aharonov bomb of both electric and magnetic types, which is essentially a graviton. Is if I'm tracking what Bob McElrath is saying, like that, it's all still consistent. So that's cool as well. But the point I wanted to bring up about the vortons is that Gould had this stability criteria where, so it's not the Pauli exclusion principle that defines what sort of quantizations are allowable anymore. It's scale invariant, but you need to essentially grow the charge. You need to input charge to be able to grow these Vorton structures. So I can drop a link to that Gould paper.
Chris, can I just ask you, for the purpose of people that don't know what a Vorton is, just synthesize that with other things that we're talking about. It's Freiberger's conceptual hook, really, isn't it?
It is, but it's really topologically the same as what we're looking at.
Yes.
Yeah.
It's another name.
The main point I want to make is topologically the same. Yeah. And more importantly, it's the generalized Maxwell equations that underlie it. So,
yeah, it will be interesting to look into it further. So I will look forward to reading it.
Yeah, perfect. Thanks, Andras.
Thanks, Chris, for your question. Right, before I go on to break the limits question, I have a question from Bob and Anne on YouTube, and that collective are asking, how does the presenter, that's you, Andras, define a field?
How we define the field?
Yes.
Yeah. Well, in our definition, it's the space-time derivative of the four potential. So for us, in our work, this electromagnetic four potential is the let's say foundational object, and you take the space-time derivative of the four potential, and that's then defines the field. I can already see that then the question becomes, what is the four potential? Okay, well, the four potential is a starting mathematical object, and I don't say that this is the ultimate truth. So this is how we understand it today, and I actually do envision that at some point in the future, this four potential will be explained perhaps in terms of space-time curvature, because I can imagine that in the future perhaps everything will be explained in terms of space-time curvature, and all these potentials and fields will be seen as different deformations of the space-time and space-time waves traveling, meaning that we are looking at the ripples of space-time itself. I can imagine that, but that will be probably 22nd century physics.
Okay, so I don't know whether that answered your question, Bob and Anne, but thank you for it. So break the limit. Would you like to take the microphone?
Yes, thank you very much. Hopefully I'm coming through okay. Actually, it's perfect that you went right in 2 questions ago into positron-electron pair separation or spontaneous generation. And my question is about the energy requirements for when we see a spontaneous generation of a positron-electron pair flying apart at 180 degrees to each other after they've absorbed 1022 kiloelectron volts equivalent photonic energy. What you're presenting here is a really fascinating model that, and by the way, fantastic presentation. Huge salutes to you for an amazing, trip through the mind space of what these particles might actually be and how they're structured on that scale. It finally kind of makes sense why these EVOs tend to take the shapes they do and why electrons can cluster together after what you presented today, because if the very shape of your particle is effectively a tiny little conduit for this larger structure. So what I'm wondering is, does the photonic energy of our input photon beams, each 511 kiloelectron volts, actually get wrapped up on themselves to then become the physical particles we know as the positron and the electron, or is that energy absorbed in separating 2 particles which already exist?
No, it is the first one. So I believe that you start from this wave, which is just electrical and magnetic fields in a trivial wave solution, and then the curved space-time makes them curve into particle-antiparticle pairs. So it is really just a wave that was there, and the wave becomes what we see as electron and positron. There was no particle before.
That is remarkable. And then may I ask a follow-up question? In terms of how we generally would generate a spontaneous positron-electron pair, we would oftentimes use matter to initiate this process by sending two photon beams in extremely close proximity to some physical particle.
Yes.
Is there a particular reason for why maybe the temporal compression or the higher stress energy density surrounding that particle would assist in this process?
Yeah, I suspect, I'm not a specialist in this, but I suspect it's the curved space-time around the particle, because the more close you are to the particle, you have a very high electric field close to a charged particle, but this high electric field, you can also understand as a curved space-time.
Right, a compression in epsilon of the variables.
Yes. I think it's this curvature that is responsible for the process.
Thank you so much for answering the questions. That was perfect.
Okay, welcome.
Okay, Cosmic Dave, did you want to ask your question directly, or do you want me to do it for you? I'm looking at you're in both places, so you can take the mic. Do you want to take the mic? Okay. I will ask it for you. So, Cosmic Dave, is he going to ask? Okay, he's asked me to. Right, so he says, do you think that consciousness can influence these fields? And is there something more fundamental behind wave collapse?
Oh, well, this question, unfortunately, I cannot answer. I don't know. And the one reason why I decided to study physics and not biology, because I thought biology is just too complicated for me, and I stick with simple electrons that maybe we can understand.
Okay, very good answer. Yes, stay in your lane. Good. Okay. All right. So, his view is, in reply, personally, he thinks they can be affected. Okay. So. There we have it. So, okay. So, Gerald, do you want to take the floor?
Hello. I don't really have a question, so for that I apologize. I just wanted to thank you for your work. You're kind of laying the foundation of how I'm going to explain some of the work that I've been doing with geometrical coils, and I love it. I wanted to say thank you. That's all.
Okay. Welcome. Thank you.
Thank you, Gerald. That's very kind of you. Right, so I'm just going to see if there's any... Right, what we might do is see if Pavel has got his speaker up. Pavel, have you managed to get a microphone working there? And in the meantime, I'm going to pause on YouTube, so you're going to get a hold frame, and I'm going to get some comments up. And what will happen is, if I can get Pavel on, then he will speak. If not, I will just do a quick overview of some of his presentations. Now, you all know my jig is I promised to do this whole process without actually ever showing you an equation. I fall flat when I started talking about the bagel game, but I did it more on a conceptual basis. It's about as far as I got. So I don't mind people like Andres stepping in and Pavel stepping in to do equations, because that means I can stick to my lane as well on the visual and observational science. Yeah, I will just show you some things that he's observed. I've already identified certain things that Andras has spoke about today that is in Pavel's models, and other things that you've asked questions on, which are potentially different between the two. And if we can't get Pavel on today speaking, I will ask him to join me here in this room, because he's only about an hour away, and we'll do another session with his presentations, and hopefully Andras can come back during that presentation and have some questions for him. Okay, and he'll have some time, I guess, to evaluate his work. All right, so for those on YouTube, I'm just going to check there's no more questions here. Okay, and anyone in the room want to ask another question of Andras before I try and do this partial switch over? Okay, Stephen's just again wanting to say your presentations are great, and had more, and you had more information in your presentation, he said, Stephen, than you gave in your 2023 paper. So he appreciates the extra context there. So thank you for that. Okay, right. So there's going to be a pause. Okay, so actually Conrad Patterson is asking, do you have a website?
No, we don't have a website.
You need to fix that.
Yeah, well, some of you know that I'm working part of the Clean HME project. So the Clean HME project does have a website, cleanhme.eu, and some of the news I post there among the Clean HME news.
Okay, so that's on one of the EU funded projects, yes.
Yes, it's cleanhme.eu. I put it in the chat.
Thank you. Okay, so I'm going to do this attempted switch over now, so it will go quiet on YouTube. Conrad Patterson says thank you for the answer. So we may have lost Pavel, in which case I'll try and get him on in my studio here in the future presentation to do his work. In the meantime, just to see if he's rebooting his computer, Stephen has put on the frame there a group of shots of the formation of a plasmac, Paul Collock's concept for the formation of ball lightning, where you get a discharge with helicity and it causes a kink instability or a series of them, and then these tear off and the current that flows around one of the loops adds to the current of the next one, merging with it until you get a large torus with a very intense current in there, and you have a separatrix around the outside, and it becomes a self organized structure. I actually don't believe it works like this, and actually one of the original authors on one of his papers wrote on one of my YouTube presentations that I gave a few years ago, 3 days ago or 2 days ago, to say that actually the elongated version was actually a camera artifact, and he's one of the authors, so there we go. I actually think it does do kink instabilities, but what we have shown, and I showed you at the start of this presentation, was that you end up getting these twisted pair structure coming out, which has a closed loop at the top. And we actually took that in David Boutilliers' experiments. We literally showed that. And I think what happens is it twists through like 90 degrees, and there's a what Jay Roth calls it's a kind of like a pinch or a bulge instability, and that causes the pinching off, similar to what occurs in the original work by Bostic. And they're actually 90 degrees, and they then lock on to the magnetic field with their own poloidal magnetic field around the original loop, and then these are just made, and you end up with a Tor of Tor. And as more energy is put in through helicity, the same thing occurs on the subtors. So I think you end up with a fractal toral structure being made. But I'll do that in a separate presentation. So I think that's probably enough time to see if... Okay, so we're not going to get Pavel back. So what I'm going to do is I'm going to share his website and a couple of his presentations, his PDFs, and then we will do a separate session another week of this. So of his work specifically. So I'm going to share that now for the people. You can see it now in YouTube, but I'm going to share it for the benefit of those on Zoom. Okay, so for those on Zoom, can they see what I'm looking at now?
Yes.
Okay, great. So this is Pavel Ozmira. He was associated with a couple of universities here in the Czech Republic, predominantly the Technical University here in Brno, where I live. And he has been very much onto this toroidal structure of matter for a good proportion of his life. And you can see various different things that you might identify with this vortex here and so forth. And he actually has a ring model of atoms, and he's actually producing a kid's toy where like the sticks or Lego, you can join these things together to learn about his particular model of the atom. And on his website, so this is his main, if I actually go here, no, not that, on his, maybe just go to the root here. You can see here is a professor of computer science at Brno University of Technology, and that's where he's at. And you can see these toroidal interacting structures here and some very nice graphics. I think some of these graphics were done by another Czech person called Pavel Werner, but he has this link here called publications here, and if we click on that, You can see a whole series of publications going back to, when is it? This one's 2009. And we're going to have a quick look at some of these, but I'm going to leave the equations and that side of the discussion to him when he's about at another time. And I don't know which one I'm going to look at here. It's called Vortex Ring Fractal Structure of Atom and Molecule. So this is, I think, a later paper of his. And you'll see some of the other discussions similar to what we have been discussing about the history of vortex matter organizations thinking for like the substructure of matter. Anyway, he says, this chapter is an attempt to attain a new and profound model of nature's structure using what he calls the vortex ring fractal theory, VRFT. Scientists have been trying to explain some phenomena in nature that have not been explained so far. The aim of this paper is the vortex ring fractal modeling of elements in Mendeleev's periodic table, which is not in contradiction to the known laws of nature. We would like to find some acceptable structure model of hydrogen as a vortex fractal coil structure. This is basically what similar to what Andres was discussing of the proton, and a vortex fractal ring structure of the electron. So this is kind of how I view the electron. It's a vortex fractal ring. So this is why Pavel was his work was forwarded to me when we found these structures and their imprints and the physical manifestation of them last year. So this is different to Andras's model, but my view on if you go back to my original presentation, I was saying that the Zeta-Bewegung motion is because each of the vortex fractal rings is self-similar, and it kind of like moves things around it and around it. So it goes up and around. And if you think of that in a fractal nature, you end up with the Zeta-Bewegung motion around it of something. And is that the
that's the proper German pronunciation.
I can't say it, but thank you for correcting me. I'm gonna. Oh, that's nice. Okay. Oh, this you've got the motion on your coil there. That's very nice. So Gerald is, for those on YouTube, Gerald is showing. Right, I'm gonna put Gerald up here so you can see him. He's showing a image of his coil here. So he's actually building something with that kind of electrical current flowing through it. And he's got a whole bunch of coils. Wow. You are the coil master, I have to say, Gerald. Wonderful, wonderful. Do you want a section at the end and show these off full screen? I think that would be nice. Yeah, okay, we'll do that. All right. So, yeah, so I think there is a way to rationalize the thinking of Andras et al. and Giorgio Vassallo with the vortex fractal ring structure of the electron. And in fact, it's actually something similar is done by Pavel Smira on his website. In fact, if you, I think maybe I can show you. Is it here? No, it is on his publications page. This is how I kind of imagined it. He's actually got the fractal structure here. His interpretation. This was done by Pavel Werner, and you can see he's actually done the helical movement going round as a shift from one to the next to the next to the next. So it's not quite showing how I imagined it in my head and described it in 2020, but it's pretty close. Anyway, so back to his work, and I recommend you go and have a look at his site. And so for those that want to know, it's Pavel. That's PAVEL. OSMERA.cz, and you can get to his papers. So he works out the spin of the electron, and he has the old classical sphere model here and this orbiting thing going on here. He says there's a relationship between the proton and electron here through their magnetic lines, and he talks about how the magnetic lines are formed and so on. So it's a lot of calculations in here, and this is the sort of thing that it would be interesting to see what Andras's view is of these things. And here we go. This is the motion here leading to that spin of the positron or the electron, respectively. And if you go down here, you can see here the vortex fractal structure of the proton. So he's got the coils and then they're offset like this. And it actually extends further than that. When we go down here, this is the electron. So in his model, he goes further than I went in terms of using the fractal model to explain properties of the electron. I haven't verified what he's done here, but it kind of makes sense. So someone asked, what causes the magnetic vector to be orthogonal to the electrical vector? Well, he's actually got that in here, and he's saying the -4 electron subtor structure is the electric line, and orthogonal to that is the -3 fractal subtor structure, and that causes the magnetic line. Okay, so you've got the overall E- electron structure here, which is the whole thing, and then the -1 is this level, which is the subelectron, and then here you got the -2, which is the subelectron. Okay, and then he's basically doing these to say, like, if you can imagine that these rings are substructures of substructures. So and if you can imagine that this goes ad infinitum, then the fine resolution of that, if something was traveling around this, as I was describing earlier, it would end up with that thing in German that I can't say, and we're going to call it Zitterbewegung. if you can imagine. All right. So I want Andras's opinion on that. Like, this is how I imagined it in my head, and I didn't realize there was someone already out there that had thought about this. Is there any way you can think that might be rational? And it comes down to what is field, I guess.
Yeah. So, well, the first comment is that the charges, they have to move at the speed of light. I'm not sure what these whether the charge is on these rings or where exactly is the charge, but from our perspective, wherever the electric charges are actually located, they have to move at the speed of light, creating the Zitterbewegung.
Okay, so that's a first question for him, I guess. So that's a great question for him. Okay, so he has this concept of the electric field and how they fit in, what electric rays are, and so on. So it's very, very detailed, that the level he's gone down to physically explain these things, whether they're right or wrong. I think it would be easier to understand when he's talked through how he sees things. And so, and again, we see this number cropping up here, which we were talking about earlier with Andras, and again, his model explains the observable data that he has selected. You know, we've got 0.89 here and so on. So very similar things going on. Now, with these structures, he then goes on to show the various structures as the other author did that I started out by showing here. And he actually shows down here that the proton is a fractal coil. So you have a number of windings going around, but he's then taken 2 of these windings here, and you can see that the 2 of the windings there actually have a coil around there, and then they've got a coil around. So he's applying the same principle to that. And I guess it's like, at some point, how far do you need to reduce it to explain the observables? And I think, Andras, where you're coming from is you're stopping short of considering any fractal level below what's necessary to explain the data.
Yeah. So the level where I stop is what we get from Compton scattering.
Right.
So for me, the Compton scattering is the radius that is given by the Compton scattering is the fundamental level at which I stop.
So you're looking at the radius that's basically across this structure here.
No. I would say the radius that is inside the line.
Okay, right, yeah.
So or you can consider it as the thickness of the line, basically.
Right. Okay. Excellent. So again, that's something that would be nice to rationalize between your work and his, and where there may be some agreement or disagreement. Okay, so that's one paper. This one's got a little bit more graphics here. This is vortex fractal ring model of hydrogen atom. This paper is an attempt to attain a better model of nature's structure using vortex ring fractal theory. The aim of this paper is the vortex ring fractal modeling of the hydrogen atom, which is not in contradiction to the known laws of nature. We'd like to find some acceptable quantum model of hydrogen atom as a levitating model with a ring structure of the proton and ring structure of the electron. It is known that the planetary model of hydrogen is not right. The quantum model is too abstract. Our imagination is that the hydrogen atom is a levitation system of the ring proton, so and the ring electron. So he goes into the mass. Here you can see the torus structure of the, I guess, the electron or matter with spin 1/2. Okay, so that's how he's deriving that. And here he's looking at the fractal structure and how he describes what's going on with these graphics in other papers in detail. I'm not going to go into that right now, but this is his levitation model of what's going on, and you would argue that this maybe is not too dissimilar to what you're saying, except that the orbit is around the collective center of mass of these two particles. Yeah, and that's essentially, so like, you know, the mass of the proton is vastly higher. It's 1,840 or something, right? Bigger than the electron, and so you could imagine that the center of rotation is actually quite close to the center of the proton, right?
Yes. And what I would like to also say for the so that there is no misunderstanding, that this Bohr orbit that I showed is just for illustration, because the proper solution of the wave function is given by the solutions to the Schrödinger equation, which has the orbital component and the radial component. So I'm not contradicting quantum mechanics in any way. I just want to emphasize that my illustration was a simplification, but there is also a radial oscillation.
Okay. So I think what might be helpful is, because I've done 3D animation since I was 16, that maybe I can work with both you and Pavel to come up with better visualizations, which, you know, if people can just understand things immediately from an animation, I think it really helps. And okay, so great. Okay, thank you for that clarification, Andreas. Again, we see this structure reappearing here, and he talks about how that adds in all these different constants and the energy here and the spectrums, and how that all fits in with his model and so on. So it really would be great to have some people who are very interested in these aspects at this level delving into this. So and that's why I think it's important, Andres, that you have a chance to look at this in detail. So the fractal dimension of an electron, and again, he's deriving the dimension of an electron here. So we would like to find a better and plausible structure of the electron as a torus and fractal structure. However, it is in contradiction with generally accepted knowledge, where the electron has no structure. Actual properties of the electron cannot be explained by point-like models. This was the same point that was being made by Andras. This paper is an attempt to improve our previous calculations of the radius of the electron and its fractal dimensions. The vortex fractal theory could possibly help with explanation of what charge the electron, the proton, the electromagnetic field actually are. So we've got this image here, and then he's starting to break it down in the substructures here. This is forces between two subelectrons inside the electron here. And I'm reminded of a New Scientist paper that I think it was from 2001. I have it over here. When I was going through my New Scientist collection here, I think this is the one. One man thinks the electron has been split. If he's right, it's curtains for quantum theory. So yes, this is from, no, it wasn't quite 2001. This is 14th of October 2000. So there we go. back in 2000, I thought, I need to save this document. Maybe it'll be important one day. And it actually describes how they did it. It's quite a fascinating paper, actually. So is there substructure? I don't know, but certainly Pavel thinks there is. Okay. What else? So like I say, this is... so here we go. Example of ring structures. This is a hydrogen molecule. So you've got your two covalent bonds with your electrons here and the protons. Now, what would you say was the... I mean, it doesn't really have an orbit, does it, here in this case? Or how would the orbit be here, Andras, if this was the model?
Yeah, in my case, I just see that the distribution of the electron is as described by the Schrödinger and Dirac equations.
Right. Yeah, you don't see it as specifically as a ring.
No.
Yeah, okay. So because you in your case you're looking at the other more spatial aspects. Yeah.
Yes. Yeah. So that in our case, the internal structure of the electron is this ring, and the kinetic motion of the electron is along the axis of the ring. But when it forms a standing wave, it has this spatial distribution in all directions of the space, and in the end, it's as defined by the Schrödinger equation.
Yeah. Okay. So this is another point of coherence between your two concepts here, where he has the proton here, but the electron is inside, forming the vortex ring structure of the neutron. So here,
yes, that's exactly the same.
Yeah, it's exactly the same. Yeah. So there is a lot of commonality here. I mean, it seems natural to think that to create a neutral charge particle, you would need to have these things where the charge was basically incident. So otherwise, they would have some polarity to them, wouldn't they? So, yeah. Okay. So that's great. We've got some consistency there. And again, that's that. And this was his latest paper that he sent me today. And I hope that this was going to be what he was talking through. But again, it's just more detail and some closer up diagrams. But anyway, I encourage people to look at those. I encourage you particularly, Andras, to look at that. I'm going to unshare now. I'm not the expert on his work, so I'm not the person to be taking questions on that. But I think it's definitely worth looking at. Okay, so I want to close out and take last questions. But firstly, I wanted to talk. George Vassallo is watching, as far as I understand it, but he says his English is not good. He was very, very meek, and he said that there's several things that he considers that this shows, and I said that I would read it out. So I'm actually going to copy it into a document here, and then we can look at it separately. So let me do this. Okay. All right. So maybe I can make that bigger. Okay. All right. So he's saying that Occam's razor is a practical epistemological tool. Now, I'm going to ask a question right at that point for people that don't know what an epistemological tool is. Andras, what does that mean?
I'm not a philosopher, but what Occam's razor means in plain English is that among all the possible solutions or models, the simplest one is probably the correct one.
Yeah, thank you. He's then saying that space-time Clifford algebra CL3-1 open brackets capital R is the best mathematical tool in theoretical physics. What does that mean?
Yeah, that just means that what mathematicians call this CL3-1 Clifford algebra is the geometry of space-time. So if you work with geometry of space-time, then the mathematics naturally follows the physics.
Okay. Then he says natural units greatly simplify the equation structure.
Yeah, natural units means that instead of using SI units, we choose speed of light equal 1 and the Heisenberg constant h bar being also 1. So h bar equals 1 and c equals 1, simplifies formulas.
Okay. So electromagnetic 4 potential is real, independent, physical entity. Now, I think you tried to answer this before. Do you want to have another shot at it?
Yeah. This I did not talk about in my presentation. So in electromagnetism theory today, the consensus idea is that the electric fields and magnetic fields, the E and B lines, are the only measurable quantities, and the potential is actually not measurable directly. You can integrate electric field and then get potential, but you cannot measure potential directly. So now Giorgio's opinion, and I share his opinion, is that actually elementary particles do measure the potential, because the electron's mass and the proton's mass is related to their potential. So in that sense, we say that it's not true that only electric and magnetic fields are measurable. The potential is also measurable, and elementary particles' mass is actually a measure of their potential.
We know it's real, don't we, because of the Aharonov-Bohm effect?
Yeah, that's another aspect of it, yes.
Thank you, Larman, for the interjection there. Did you want to extend your question there, Larman, or your comment?
Well, it's just, it's quite well known that there's, I'm not, you can look it up, the Aharonov-Bohm effect is a kind of a modification of the dual slit experiment, which shows that the vector potential is a real effect on the interference fringe sort of result. And it's not the magnetic field that's affecting it, it's the vector potential, exactly. So it's something you can look up, but it is quite well known that the vector potential, the 4 potential, is a real thing. It's not just electric and magnetic fields that can be detected.
Thank you. Did you want to reply to that, Andros?
No, that's fine.
Okay. So 5, the 4 divergence of the 4 potential is a real scalar field that is not always 0, i.e. Lorentz-Coulomb gauges are not always applicable. Do you have a comment for that?
Yeah, this is what I explained,
yes.
that we have a electromagnetic scalar field as a real physical entity.
6, gaugeless Maxwell equations reveals the nature of the electromagnetic sources as the 4 partial derivatives of the scalar field. It's again...
It's again the same. So gaugeless means that we don't apply the electromagnetic gauge condition, and briefly, physicists have invented the so-called electromagnetic gauge to force the scalar field to be 0, and we don't want to do that.
7, D'Alembert, I'm probably saying that wrong, but it sounds French because of camembert. D'Alembert wave equation can be applied to both charge density and scalar field.
Yeah, it's just another way of saying that we have both scalar waves and traditional transversal waves.
8, the electron can be modeled as a current ring generated by a massless charge that rotates at the speed of light.
Yes. I don't like here the word massless, but yeah, this is the model I explained.
Yeah. So when he's saying massless charge, the actual mass is coming from the energy of the charge, or the...
No, that's why I don't say I don't like it, because the mass is always comes from the overall electromagnetic field. The mass is not in a point, the mass is in all of the field in the space.
I mean, it's the space-time distortion.
Yeah, exactly. So that you should never think that mass is in one point here or one point there. The mass is distributed in all of the field.
The charge quantum E is always coupled to a magnetic flux quantum H over E.
Yes. So this I did not talk about, but one question that comes up is why are the electric charges quantized? Why don't we have a half elementary charge or 1/4 elementary charge? And where we got with the theory so far is to demonstrate that whatever the electric charge is, there is a corresponding magnetic flux, and the elementary charge and magnetic flux are related in such a way that if you have elementary charge E, then the corresponding flux is H over E, where H is the Heisenberg constant. So in that sense, you explain why there is magnetic flux quantization, then you know why there is charge quantization, and vice versa.
Very good. At 10, the circular helicoidal trajectory of the electron's charge can be encoded using a single spinor of space-time algebra. That was your opening gambit, right?
Yeah. Well, it's just a way of saying that if you use Clifford algebra, then you don't get lost in the notation. You can express things simpler.
Do you say spinor or spinor?
Spinor.
Spinor, okay. Spinor of space-time algebra. Okay, 11. The charge orbit radius is equal to the reduced Compton wavelength.
Yeah, this is what I explained in the electron model.
So 12. The fine structure constant is equal to the ratio of charge radius and charge orbit radius. Yeah.
This is the big unknown. I have shown you these ratios that have this amazing coincidence, but in the end, this is one thing that I would like to understand, and we don't know yet where exactly this number 137 is coming from. So that's still a puzzle.
Yeah, right.
That constant. Oh,
hold on, sorry. Who were you commenting, Alex?
sorry, I'm just agreeing. I mean, the constants, that's the key. When they pop up and we find out what they're really coming from. And that's what you're on the hunt for. Sorry, I'm enthusiastic.
No worries. It's great. We like enthusiasts. Enthusiasts get stuff done. Okay, right. So the electron massless charge has a mechanical momentum equal to the product of charge and the local value of the vector potential.
Yes. So that comes from the electromagnetic theory that when you apply Maxwell's equation, you can see that the vector potential and this internal Zitterbewegung momentum, they are related. They are strictly related.
It's all right. You've only got another 9 questions or comments by Giorgio, and you'll have passed the test. So you're doing very well so far.
All right. It shows that I have read the book.
Yes. You're the other one. Right. 14. Using natural units, the electron's charge momentum is equal to its relativistic mass.
Yeah. So this means that in natural units, that's why they are called natural. You can use mass, energy, momentum as equivalent measures.
The electron momentum, not to be confused with the electron's charge momentum, is equal to the product of charge for the component of local vector potential along the direction of electron motion.
Yeah, this I don't exactly get, but in the end, one can calculate separately the internal momentum in this Zitterbewegung motion and the kinetic momentum that's along the axis. So these are 2 separate momentum one can calculate.
The electron momentum, sorry, I've said that one. I wanted to ask it twice. It was so good. The electron rest mass is equal to the component of charge mechanical momentum orthogonal to electron velocity vector.
Yes, exactly. So it means that you have the Zitterbewegung momentum that I talked about, and the Zitterbewegung momentum defines the mass of the particles. The more massive the particle is, the larger internal momentum it has, which is somehow logical that the mass of the particle is expressed itself as the internal momentum of this electromagnetic field.
17. The value of electron relativistic mass is consistent with both special relativity and electromagnetism.
Yes, exactly, and that we describe in the book. I think that's an important result, that Einstein's relativistic mass formula you get automatically just by Lorentz transformation. So you look at this electromagnetic field configuration, you do Lorentz transformation, taking Doppler effects into account, and you get automatically the Einstein's mass formula.
The value of electron relativistic mass, I said that, haven't I? I'm highlighting the wrong one right now. I'm tired. I bet you are too. The spin is the component of free electron angular momentum along an external magnetic field.
Yeah, this is relates to that question of the figure that we had with the, remember the projection of this rotating proton angular momentum, and there it was this 60-degree angle that we discussed. So he's talking about the projected component that comes out to h bar over 2 when it's measured.
All the electron model's parameters that in natural units are dimensionless, pure numbers, are quantized. That's what you were talking about earlier, right?
Yeah. So this is an observation that when you choose natural units, you get certain pure numbers, such as the alpha, which defines the elementary charge. You get the angular momentum that's also quantized, and magnetic flux. So these kind of numbers, which then become pure numbers, such as magnetic flux, angular momentum, elementary charge, they seem to be quantized, and this is something that we still have to investigate the deeper reason, but this is not a coincidence, probably.
I'm interested in this comment here. The electron model is consistent with Aharonov-Bohm equations.
Yes. So what?
It's just
what exactly is the question?
Yeah. The electron model is consistent with de Broglie and Planck equations.
Yeah. Well, the de Broglie consistency I had a slide about where I derived that frequency.
The electron model is consistent with an electromagnetic version or interpretation of Proctor, Klein-Gordon, and Dirac equation.
Yeah, well, I
so
agree.
Basically, he's arguing that this doesn't break a lot of physics, even some physics that's not ordinarily considered.
Yeah. So this, understanding how Dirac equation relates to our model is not something one can explain in 5 minutes. It's described in our book, but the big picture that I think I mentioned in my presentation, that many of these quantum mechanical laws and formulas, such as Dirac equation, Schrödinger equation, we can actually derive it, and it doesn't have to be a postulate-based starting point for quantum mechanics. So we're not changing it. We're just trying to explain, where are these postulates coming from.
So, with all the things that it doesn't break, other than things like the particle isn't a point, what do you think it does break?
Well, for example, somebody in the comments already described about electron clustering, that if you don't have the electron model, you cannot really have a handle on the electron clustering, But if you see that there is these toroidal structures that have their magnetic fields, there can be magnetic attraction, then you can get these kind of solutions that you don't get from the traditional point particle models.
Absolutely. Yes. Right. So we maybe got some questions here. Break the limit. Do you want to take the floor?
Hey, thanks. Caught me off guard here. I was just having a conversation with David Cosmic. Definitely all on the right page. Give me a minute or so and let me just come back. Sorry.
Okay. Well, does anyone else want to ask a question before we have a look at Gerald's coils? Okay. Well, thank you, Andras. For I think you only got stumped on one question. Not really. So
did I pass the test?
I think you got 21 out of 22. So a huge round of applause for our main speaker today, our guest speaker, Andras Kovacs. Real huge hand of applause.
Thank you.
Full respect. You definitely know this subject, so that's a huge thumbs up. We're getting some silent thumbs up from those people. So really, thank you very, very much. It's been really good. So break the limit. Are you ready to ask a question? No. All right.
Actually, I think it was pretty well answered. I was curious though, just in this recent conversation, we're talking about this idea of basically synthesizing virtual particles by using these crossed product fields. And with this model, it seems like because we are just taking photonic energy, which we already have a cross product stress energy in, say, our mode of transport at velocity c, right? And those things, those photons, whatever they are, can become physical matter when they wrap up on each other because of the higher stress energy density, becoming real particles. So we were wondering, could we synthesize virtually large particles or sustain them temporarily? It seems almost like the original bagel coil experiments did exactly that. And, I'm just kind of wondering where the limits of this are in terms of what we could use for propulsion or gravity control. This isn't really a specific question. It's more just a general kind of overview of, can we synthesize new types of synthetic matter to do really interesting things?
Well, I don't know what Andras wants to say,
I really don't know what to answer specifically. I think that this is very interesting topic to experiment with these bagel game type of setups in these fractal coils. I did not do those kind of experiments. I'm doing other type of experiments myself. But if somebody is interested in experimenting in that topic, that's I think is a very interesting subject.
And from my point of view, ever since in 2017 or 2018, when they started taking apart the first Lion reactors, I viewed the things that were interacting and making these very highly defined boundary cuts into the fused quartz and other parts of the reactor, and they were exactly either in line with the solenoid B field or orthogonal to it exactly. They struck me as macro quantum objects. You're seeing something on observable with your own eyes scales that is a self-similar structure of something that actually exists in nature at a much smaller level, almost like when you're looking at crystallography and you're looking at diffraction patterns, you're actually seeing a reflection of the structure that's very, very small but big, like almost like a hologram type aspect. Whereas rather than in a hologram, you can see the whole hologram and you break it into little pieces and you can see the same hologram in the little piece. It's kind of the other way round. And this is where Chukhanov describes his ball lightning as a macro quantum object, and Ken Shoulders ultimately said that electron validium wasn't that, and it wasn't charged clusters either. What you ended up with at the end of the day is an exotic vacuum object. And a normal vacuum object, in my view, is a thing like an electron and a proton, right? So if what is an exotic vacuum object? Well, it's like a particle that you've made. And then if you have a particle that is on a completely different wavelength to most other mass, then for me, it doesn't surprise me that may have little interaction with ordinary matter, because it's almost on a completely different frequency level, if you know what I mean.
Yeah. The one comment I would like to add to that I had one experiment where I was seeing these strange, almost macroscopic phenomenon, where I was inspecting strange radiation tracks under microscope. And so in that case, I had a CD disk where I used next to the reactor a CD disk with the idea to then observe the strange tracks. And then when I was, these CD disks were next to intense electric discharge. And then when I was looking at it under the microscope had LED lights that was lighting the surface. And what was very surprising is that these tracks, they did appear upon the interaction of the light. So during while I was observing it. So that the point was that there was some object structure that got stuck on the disk surface, whatever it was, and when the light was shining on it, then it made this macroscopic tracks, and I could see these tracks moving under a microscope, and they had the size on the order of 0.1 millimeter or something like that. So almost visible by eye, and that was very, very strange. Whatever it is that it does this.
Well, it's interesting you say that, because I don't know. I haven't actually published the presentation yet, but this week's presentation with the Russian group is talking about work where they are doing spark discharges inside a tube which has a wound optical fiber around this tube, and they're passing laser light down it. And this was sprung off earlier work that was then expanded by Alexander Shishkin. And Alexander Shishkin shared some comments on this with his presentation at the Russian conference last year, where he was saying that these, whatever they are, can be moved by laser light and by light in general. And he says that a lot of Lehner experiments where they're using light to stimulate the reactor could be because it's taking charge clusters out of the air, and they're traveling along with the light beam, and then they are aggregating at the impact point, and that's triggering the effect. And it's not the laser energy per se, and it's not the metal which is hydrogenated, it's the actual interaction of the charge clusters that are being aggregated from the air. And so this gives you a way where you could stimulate reaction by literally having a discharge and firing laser beams through it towards your target that you want to stimulate the Lehner reaction with. So, and these kind of things have been done before. And so then you get to the point that Shishkin is saying that the charge clusters are basically static electricity. Well, what is static electricity? Well, it's the same thing as an EV. In that, because EVs are born out of discharges from static electricity. So, there's a lot of convergence in the thinking going on, and so what you were saying, Andres, I think it kind of aligns with that. So imagine if you had a charge cluster in the the most basic form. You had a lot of static electricity on a particle, and then you're hitting it with the light. Is the LED light enough to cause the movement of that static electricity? Well, that's exactly what Shishkin is arguing that he's currently working on. He's actually said that previously his thinking of using a laser actually came from previous work where they were using an LED. And, maybe an LED, the lights typically, like on this microscope I've got here, they've got a whole bunch of LEDs around. That's kind of what you're talking about, right? Yeah.
Yeah, exactly. It's like that.
Yeah. So the LEDs could be interacting in the way that Shishkin is describing with the charge cluster, and it's causing it to maybe get excited or destabilize or literally move away from the light. So yeah, very, very interesting finding. Thanks for sharing that with us. That's really if you would, it would be great if you could send an image of that track that you captured.
Yeah, I will do that by email after.
Fantastic. I'd share it at the bottom of the blog. Okay, so we've got a couple of comments here. What is it? Blah 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 blah. Oh no, they've moved off. I can't see them anymore. Okay, that's way. Okay, all right. Well, I think we're finished. We had about another half an hour to go, but I think that's probably enough for this evening for everyone, if that's okay. Are you okay with that, Andres? Okay, fantastic. So I'd like to thank Andres again. A big clap again for Andres, especially as he passed the test. And yeah. And just to close out, Gerald, do you want to go full screen and share and show some coils and what you think they should do and what you have seen them do?
Sure, I'll do a quick show and tell because I have a presentation for this, but I'm prepared to show it. So, yeah, I just do a quick show and tell. This is the foil that I ever made. This is a vortex coil. The design was by a man by the name of Mike Powers. My inspiration came from John Bendini for building these coils. This was my second coil. This one took roughly a day and a half to 2 days to one. It has 750 feet bi-firely wound. In other words, one way and then the other. So there's 750 feet on either side. And then I've showed you this one earlier. This one was wound with galvanized wire for a specific purpose. All these coils are vortex coils, and they all have different purposes and different wind configurations. I built over 175 different coils, mapped out their geometries, their fields, what they do. This particular coil here, you can put 12 volts, 12 watts into, basically 1 amp, and I can light a 150 watt LED grow beam at about 90% its power, just on 12 watts through this coil. And then there's this one. And this one here is made out of 2 different types of metal. It's a copper and an aluminum that's been coated. And then this one here is the one that I use for electroculture. And as you can see, it has multiple layers of winds on the inside. This one was an interesting wrap, to say the least. And I'll show you one mildly bigger one, but very simple to see. And they're all based on geometrical form. And do or would like more of an in-depth presentation, please contact me, Bob, or whenever you would like, and I'll do a full presentation on what they do, how they're made. I've written a book on how to build them, how to wire them. And the notes that I've gotten from the experiments and these devices, they've filled 4 binders. So there's a lot that I've done with them. I've done electroculture experiments, power generation, carbon capture, magnetic confinement experiments, PEMF healing, and one that I don't talk too much about, but there's a propulsion aspect to certain coils that I've built that I'll get into in the future, in depth by far. So that's my presentation.
Awesome.
Thank you for the
All
time.
right. Well, let's try and set that up. Stephen's got a question. Gerald, can you put a quartz crystal in the middle and make it react in some way?
That's not an experiment that I've done, to be honest with you. It's definitely something that I can put on the list for the future.
Okay, awesome. So, Gerald, thank you for that. I'm going to call it a night, and we'll have you on in your own session.
Awesome. Thank you very much for your time.
Thank you very much. Thanks a lot. Thanks for everyone on YouTube. And I'll say, buenas noches, dobry noc, good night.
Thanks. Good night.
See you guys.
Good night.
It was awesome. Thanks so much for hosting. Can't wait to get into temporal mechanics in the future. That'll be a fun one.
Yes, torsion mechanics is a beautiful thing.
Awesome. All right, guys. I'm going to call it off. Bye.
Record.